Hello, sir.
Yes,
Sir,
Lapsa,
shall I start?
let us wait another 2 minutes.
Oh, okay.
People are joining.
Okay.
Let us start of just 10,
Oh,
5.
okay, sir.
Hello, sir.
Hello.
You will start now. Hello.
Hello.
You will be starting the program now.
Yes, yes, we will be starting in 3 minutes time.
Oh,
People are joining.
oh yes, I am joining. Then I have to pause.
Okay, okay.
Okay. Thank you.
Miss Rupan Rani Dash, please put off your camera. I'm repeatedly requesting you to put off your camera. Rupan Rani Dash.
Hello.
Yes, Miss Fernandez, what is your problem?
Uh, we should write our attendance. We should do our attendance, sir. No need.
If it is to be done, we will give you the link and kindly keep your camera in off mode always.
Okay.
Nilkamal Nath, please put off your camera.
Okay.
Participants are requested to put off your camera throughout the program. Attendance link will be given maybe 10 minutes after the lecture starts.
Okay.
Lapsa, Lapsa, Gulab sir?
Yes, sir.
Hello, Gulab sir.
Yes, sir. I'm here.
Please start. Please start.
Okay, sir. So, a warm good morning to all of you present here. Our respected head of the Department of Physics, chairperson of the program, respected invited speakers, faculties, and all the participants. I welcome you all to the second day of our international webinar in nanoscience and nanomaterials. Today we have one technical session which includes two invited talks. So without further ado, with the permission from chair, I would like to invite our first speaker. Ma'am, may I?
Yes, please go ahead.
Okay, thank you, ma'am. So our first speaker of our today's technical session is Dr. K. Jugeswar Singh from Indian Institute of Science, Bangalore. And the topic of discussion is transport phenomena on organic semiconductors. So to give a brief introduction about our speaker, Dr. K. Jugeswar is working in the Department of Physics, IISc Bangalore. He obtained his PhD from IISc Bangalore in 2009. He has done his postdoctoral from Center for Material Research Division, CNRS, Orleans, France from 2009 to 10, focusing on lithium-ion batteries. Solid State Structural Chemistry Unit, Indian Institute of Science from 2011 and 12. Baylor University, Waco, Texas, USA from 2012 to 2013 with focus on bioenergy. He has publications in various journals of international repute such as Scientific Report, Physical Review B, Chemistry of Materials, Electrochemistry Communications, J-Physics, Condensed Matter, Material Research Express, Result in Physics, Integrated Ferroelectrics. His main research areas are condensed matter physics, nanoscience, etc., and has done remarkable work on transport phenomena on organic semiconductors. So I'd like to request our speaker, Dr. K. Jugeswar Singh, to kindly take over the platform.
Hello. Hello.
Yes, sir,
Hello.
we can hear.
Can you hear me?
Yeah, sure.
Oh, so now what I have to do, I have to present, correct? Now here. In the screen. Is it came now? Are
Yeah,
able
please.
are
Yeah,
able to
please.
see my screen?
No.
No. Okay, 1 minute. Yeah. Here.
It's coming. Full screen is coming actually, not the
Okay,
presentation.
so I just planned 1 minute. Something is going wrong. Okay, I just because it's slow, so net is slow, so I'm just switch off my video. Are you able to see my screen? I'm not able to see.
No, it's not visible.
It's
Dr.
not
Judy.
visible.
Yeah, it's not yet.
Okay, let me try again. Okay.
From present now, you can just go to that particular window which you want to present. It's coming. It's coming. You may go to full screen mode. It has come.
Okay, now yeah, I'm going to first. Where it goes. Okay. Is okay now?
Yeah, it's perfectly okay.
Thank you. First of all, yeah, thanks for inviting me in this webinar, Nanoscience and Nanomaterials, on the 16 and 17 November, organized by the Assam University Department of Physics, Assam University. So I would like to thank Professor Indrajit and his team for organizing this webinar. When Professor Indrajit asked me to give a one talk, then the next day he called me. The topic will be from on the nanoscience and nanomaterial. Then I replied that I'm not working on nanomaterials. Mostly my work is macro, which is in devices. So he said, it's okay, fine, no problem. If something is related to the nano, then you can just go ahead. So thank you for that, Professor. And thanks the team which works this this webinar. Are you able to hear me? Hello?
You are audible, sir.
Are you able to hear now?
Yeah, you are
Okay.
very clear, and presentation is also very clear. You need not worry.
Okay, thank you very much.
Please go.
Yeah. Now here, this I'm showing a photo. This photo is the Talent Development Center. This is the department of Indian Institute of Science. Is a new department, which is located 230 kilometers far away from the Bangalore. The place is called Chalakare. In that place, IISc has a new campus just started. It is about for 1,500 acre. It is surrounded by 3 central organizations, which is just developing. They are Babai Atomic Research Center, Defense Research Development Organization, and ISRO is there, which is going to be, I guess, which is going to be the India's new science city after 10 or 15 years. So this is the place where the teachers do training, and I also work there most of the time. So today's topic, apart from that one, today's topic is for transport phenomenon in organic semiconductors. So yesterday, many professors like Dr. Lyson Tomba and professors like for Dr. Syed Arshad Hussain, Professor Sangam Chatterjee, they speak very well topics, and topics are very nice and interesting, and we learn many ideas, and we share their views, very nice. So today I'll share some of my views, which I do on my research, this transfer phenomenon in organic electronics. What is meant by these organic semiconductors? They are plastics, which we know that since organic materials are plastics, you have seen for plastic chairs, the toys, and the pillows, the cushions, and most of our material which we use is organic materials. Polymers are one of the most used material in the modern world. Their uses are and applications ranges from containers to the clothing. They are used to coat materials, wires, prevent electric shock. Very interesting materials. Now, what we do, why this material becomes so important. That's what I'm going to share a small story. This is the story which some reporter asked Alan McDermott, which I'm presenting the photo. Okay, in October 17, 2000, in the year 2000, the reporter asks, is there any eureka moment that spawned this research, means research on the conducting polymers, and how did it all come together? And why I'm telling this story is related to my topic. This professor, he replied to the reporter, he's saying that in 1975, he went to the Kyoto University as a visiting professor. And he is giving a talk in the university. There he finds there is one person called Hideki Shirakawa. After the talk, and this Hideki Shirakawa is shown a golden color, electrically conducting inorganic polymer, polysulfur nitride. Then again he said, I have something like that also, but not inorganic, that is organic, polyacetylene. Professor Alan McDermott was so surprised, and he eager to work with the Dr. Hideki Shirakawa, and he said, if I get some money for you, could you come to the US, okay, and work with me? Then the other Hideki Shirakawa said, of course, why should not? I will come. Then after returning to the US, then McDermott wrote a letter to the sponsor, to to give some money for his postdoctoral position so that he can hire Hideki Shirakawa. Finally, grant came for 20 to 22,000 US dollar for a year. Then he called Hideki Shirakawa and they start working. Okay, then once they start working, then Hideki Shirakawa then prepared some sample. Okay, in that sample, then they measured for the conductivity and they do for elemental analysis. When they found elemental analysis, they found that there is some impurity. They are thinking that if the impurity, if they remove, then the conductivity may increase. Then Shirakawa tried, remove the impurities, make pure and pure sample, polyester sample, but becomes a contradictory result. They found instead of increasing conductivity, they found the conductivity decreases. Then finally they found, oh, something is contradictory. Then what shall we do if we add the impurity? They add the bromine and wait for some few minutes. Then very surprisingly, they found the conductivity changes almost 10 to the power 5 order, 1 million. It changes. Conductivity increases just like that. Then now, since both of them are chemists, so they do not know how to interpret the result. Then McDermott realized his friend, Professor Alan J. Heger, he works in the University of California. Okay, he asked the professor to join in their work, and Heger was so excited to do something. Then finally, they worked together, and they found something very interesting. Then Heger, McDermott, and Shirakawa demonstrated the proper doping of the conjugated polymers improved its conductivity just like as usual semiconductor or metal, and they referred it as semiconducting or conducting polymer. They reported the first time in the history that the conductivity of the order of 10 to the power minus 5 Siemens per meter, that is insulating polystyrene thin film, can be increased by doping with iodine up to a metallic polyacetylene of 10 to the power 5 Siemens per meter, just like as copper metal. No doubt, it was a great turning point for a discipline of the polymer engineers that initiate the new field, organic electronics or polymer electronics. For their work in recognition, they got the Nobel Prize in the year 2000 in chemistry. This is history for the conducting polymers. Now, let's see what is conducting polymer and what is the difference between our conventional polymers. Conventional polymers, generally we have seen is we have known is a several thousand of monomer units in chain. Their most of the properties are they're soluble in common solvent, highly tractable, and electrically insulating. What about these conjugated polymers? Conjugated polymers are the polymers which have alternate single and double bond. Okay, they are almost 700 of monomer units in a chain. The pristine state is insoluble. Okay, but if doped, it can become a conducting material. Few of the conducting polymers, which example I have given you here, these are now poly to 5-dialkoxy P-phenylene vinyl. Okay, and a few are here goes up to the poly 3-alkyl thiophene. Okay, these are common that conjugated polymers. What about the electrical properties in the polymer state, ordinary polymer state? The electrical property is very, very low, 10 to the power minus 8 Siemens per centimeter at room temperature conductivity. So, what makes this material conductive? Very interesting. I told you, I have shown you the 3 states of the 3 simple carbon compounds: diamond, graphite, and polystyrene. They may be regarded as 3-dimensional, 2-dimensional, and 1-dimensional forms of carbon materials. And diamond is generally known is insulator, and its high symmetry gives it to isotope property, while the graphite and acetylene both have mobile pi electrons and are, when doped, highly isotropic metallic conductor. These are the starting of these conducting polymers. Another example for this ethylene, okay, this is a hybridization of ethylene. Broadly speaking, conjugated polymers cover the extensive portion of conducting polymers. Conjugated polymers are defined as such polymer which has combination of alternating double bond and single bonds. As we know, single bond, okay, when we compare the single bond with the pi bond, the sigma bonds are what is called more rigid or more tightly bound, okay. This typical special combination of single and a double bonds for conjugated polymer offer a unique arrangement of delocalization of charge carriers from one end to the other end of the polymer chains. This pi orbital overlap supported the continuous single bond allows a delocalization of pi electrons. Okay, double bond and electrons are called pi electron offer px, py, pz hybridization for the carbon atoms. Okay, draw the double and a single bond combination just as ethylene, okay, which I have shown you here. Such delocalization, okay, such delocalization in the C, okay, such delocalization of the free carriers in the main reason for the charge transport within the molecular chain, means intramolecular of conducting polymers. So now how we do next, okay? So how do we make these polymers to become conducting? First one, we can polymerize. How do I polymerize? I can add one monomer to the another monomer, one after one, I can add the monomers. Then you measure the conductivity, there is no electrical conductivity. Then what we do, we add dopings. Okay, we add dopants like bromine, which I will give you next within the next few slides. What are the dopants which generally will work? Or you do for electrical or some preparation while preparing the polymer itself, you dope. Okay, first you prepare the polymer or dope. Second one is you while polymerization itself you dope. Then after you can get for your electrical conduction. Otherwise, you will not get for electrical conduction in this only in this direction here. Here, few of the samples. Here, I'm not showing for my research lab because everything is available in all the places. And here we do for small funny things. This is a beaker which we cut a neck and we put for an electrochemical cell which we work. And the films here I'm showing is 10 micron thickness film, mechanically very strength. Okay. And the size you have seen here, this is almost some 3.5 by 3.5 centimeter in size we grow. Okay, we are able to grow. This is one of the examples for the polytrihexyltryptophan films. Okay, now the conductivity, if we do this one, how the films prepare, I will show you later. Okay, this is just example for how the films are made. When we dope, what about this doping? Is it same as our what is identical doping in what we know for our N-type or P-type inorganic semiconductor like silicon and germanium? What we do? These dopings are not like that. They are not replacing the electrons of the germanium. They are not replacing the electrons of silicon. It's not like that. They are not replacing. When you dope, they are not replacing any of the electrons of the host. Okay. So what do? They form intercalated, just like yesterday Professor Said had talked many things about for intercalation. Okay, they just go and sit inside the polymer chain. So when they do for here, this one is the dopants. What I do for star marks, these are dopants, and these lines, what we saw here, this is the polymer chains. They are just sit. The ions are just sit inside the polymer chains. So what are the dopants generally we do? There are two types we know for the reactions, oxidation you can do, reduction you can do, then you can get for N-type or you can get for P-type semiconductor. So depending on this one, there are few of these compounds which is for iodine, ClO4, PF6, and BF4. Generally, we used to work in the PF6 from the tetrabutyl ammonium hexafluorophosphate. So this the phosphate part, hexafluorophosphate part is the one generally we are working. But what we work for the Shirakara is for iodine. Okay, this generally we do here. This is for the doping. When we compare this one, this is the start of the electrical conductivity. Okay, it's a logarithmic ladder. Okay, Siemens per centimeter inverse. This comparison of the films what we generally people used to find. Okay, these are this what we have seen here. Polyacetylene doped with SF5 is almost close to the copper material. Okay, 10 to the power 5 quarter is not so bad. But generally, what we are working most of the time, people are working in the range of polypyrrole in 10 to the power 3 in this scale. Most of the time, people are works as for devices for semiconductor. How it conduct? Because since this is not the electrons are not replacing, not become for the majority N type, majority P type, unlike for the inorganic semiconductor. How the charges are conduct? Here is very fun game. Everybody, I'm very sure, might play this game when we are in childhood. These numbers can move until unless there is a one hole, one vacancy that is there. Okay. Similarly, what we do here, these dots, okay, these dots create in this one here. Iodine, if it is the one, the dopant which I shown here, then these bonds break and this one bond is transferred energy here, then it becomes a long, then this bond are moving one after one and flipping of this bond. This flipping of, while flipping of the bonds, what we do, charge is transfer, we can say that. So this is nothing but the conduction in the polymer. Okay. So this is how we move forward here. Next, what we are going to talk for this one, for the applications. What are the applications? Why we do this one? There are many applications. Applications are for these organic solar cells. They apply organic diodes, organic LED, organic FET, polymer insulated gate fill, okay, IGFET, I can say, and flexible display. Okay. So the polymer in the diode itself, we are made for polymer Schottky diodes, polymer for LEDs, which generally is available in the market, and now even for displays also available, largely available in the market. Now here I have shown a few pictures of flexible displays. Okay, displays made from organic electronics. Okay, the flexible OLED. The first one is Sony XCL1, the world first OLED TV. Now you have seen this Diwali, you might seen for many offer for the OLED TVs, okay, by you in a very low cost prices. So these are the few of the applications what I have seen and shown you here. Okay, next, now here this is for applications in the organic light emitting diodes. Okay, so organic light emitting diodes, in this one, the electrons withdrawn from the HOMO, okay, at anode, leaving a hole at the HOMO level. Okay, here, okay, not here. Okay, HOMO level. Injection of electron hole into the HOMO, formation of recombination near a emissive layer due to the electrostatic force, result a relaxation in the energy level of the electron, accompanied by the emission of radiation whose frequency is in visible region, that becomes for LED. Now, even though we have many applications, but there is no unique transport mechanism. Due to such ambiguity, different charge transfer models are reported to validate the experimental results performed on various polymer devices. Among these charge transport models, space charge limited current model is counted as highly recited and unanimously accepted charge transfer model for the use of organic and polymer semiconductor, which we are going to discuss. In this talk, we discuss for the brief overview of the space charge limited current, which I just said now here for this polymer semiconductor devices. Now, the charge transport here generally we used to say is for the metal polymer interface bulk limited injection Okay, then more unique spacers, model type spacers. These are some of the listed models which people use to analyze in any of the source transport phenomenon in the organic semiconductor. Okay, but before doing this one, what we want, I want to put a few words here is that conducting polymer offer large number of topological defects as disorder. These defects, such as breaking of bonds in molecular chain, torsion, addition of both internal and external impurity, are produced during the synthesis of polymerization and causes to provide electrical traps for conductivity between the molecular chains. Thus, disorder in conducting polymer present localization free carriers inside molecular chain. Okay, therefore, intermolecular chain transport requires hopping free carriers from one molecular chain to another molecular chain. We can say the charge transport in polymer in combination of both intramolecular and intermolecular transport properties. So now, coming back to the first one, the metal polymer interface. Why this is so important? If we make a polymer, or what is our ultimate goal? Ultimate goal is we are going to use as a device. When we have to use a device, what we do? We should make some contact to make the electrical connection. The polymer film, now what we prepared is now anyone we are going to prepare the polymer, it has to be tapped with the metal contacts. So that means there must be a interface between the metal polymer junction. So now here, once we tap, what happened? The work function, okay, the work function of the polymer and the work function, or you can say the band gap, okay, band gap, or from conduction to the vacuum jumping, or metal and the semiconductor, they are not the same. They are in this one, this part is for the semiconductor and this part for the metal. So they have different. Here is now the valence band, and here is the conduction band. Here is the Fermi energy, depending on either you can make Fermi energy maybe here or maybe here, depending on is the N type or is in P type. And this is the vacuum where it can be, electrons can be removed, knocked out from the space, actually from the polymer to the space, or it means free, just like for here the work function from the metal to the space, okay, to the vacuum level. So this much, this is we call for the work function. All right. So now this is the Fermi energy of the metal, and here the Fermi energy of the semiconductor. What happens if they combine together? If they combine together, when they join together these Fermi energies, okay, they will be lined up. Since the Fermi energies are lined up now here to here, Fermi energy line up, then the conduction level pulls down. All right, by giving this, the gap should be the same. Then since this is coming down here and this is a work, here is a vacuum level is here, this vacuum level pull down, there is a barrier height, a gap will be there. If the thickness, if they are more and more contact, proper contacts, means these deltas are more and more smaller, then finally you will get this one. This is the ideal case. Okay, as the gap delta decreases, the electric field in the gap increases, and increasing negative charge is built up at the surface, and equal and opposite charge positive must exist in the semiconductor depletion layer. Okay, and this will give for what is called for potential barrier height. Okay, now this, once the polymer, the band is formed, then there are many different ways of the metals you may be used for contact, making the contacts. Okay, so in that making the contacts, we have here many metals we may be used. What for that one metal, the work function for these polymers, then we can be in the polymer 2 to the 6 electron volts. Okay, sorry, the for metal work functions. The value of the metal work function is generally very sensitive to the surface contamination. Okay. Then this is for the 3 fundamental different contacts are described. First one is for neutral contact. The similar behavior with work function. Neutral contact means the work function, so the Fermi level, Fermi energy of the metal and the Fermi energy of the semiconductor, they are equal. Then this contact contacts we call for, say, neutral contact. Then now here, this is for blocking contact. In the blocking context, there are two types where the Fermi energy is lower, Fermi energy is upper, so that we can call something called for defining for a work function of metal is more than the work function of the semiconductor. Another one is work function of metal is less than work function of the semiconductor. So these are the two types of the blocking. And another type which is similar to this one, we call for in another name we call for electron blocking, hole contact, and hole blocking. Electron blocking ohmic contact and hole blocking ohmic contact. These are the same phenomenon, which the idea of the people use different terminologies for different ideas are there. So now we are not going to in detail for this one. These are general phenomena, general conclusions from the system here. So here the contact type, contact may be blocking for electrons blocking, electron blocking contact, hole blocking contact. What are the conditions? What about the current conduction is injector limited? It is denoted by injector limited. Another one is for bulk limited. Right. So now this is for image, another field lowering. This is also, I'm not going to talk much here. It's saying that the barrier height, when you put dop on the ion or any dopant or electron put inject to the film, then what happened? Then the image is formed in the other side of the metal. Because of this one, the barrier will be pulled down. This is showing here. So now the most important part of the topic is now today will be here. Bulk limited and injection limited current flow. What is meaning by bulk limited? Once you make the context, then you have to apply the electric field. Then once you apply the electric field, electron or hole has to flow depending on the context. That's what the two things we come here. The limitation of the current of the polymer can be classified. Now here we said here is injection limited or bulk limited current flow. For injection limited, the limitation of current through a polymer is imposed by non-ohmic metal polymer interfaces. Your metal polymer interface should be non-ohmic. While the bulk limited, the limitation is imposed by the bulk properties of the polymer. Second one is if the conducting polymer is sandwiched between the two electrodes and any one electrode offers low barrier. Low barrier height means they can go very easily. That is ohmic response to the polymer metal interface. Then the injected carriers form electrode forms a space charge region consisting a large number of injected carriers and equilibrium free carriers inside the polymer. In this bulk method, as the mobility of the carrier is very small, therefore traversing of the injected carriers from one to the other electrode, more and more charges are injected. When the external field is applied, further charges are injected from the low barrier electrode to the polymer, and an equilibrium state is reached when the injected carriers are comparable to even higher than the free carrier concentration. At this stage, the flow of current is referred to as space charge limited current. We may be a little difficult to understand this one, but I can tell very interestingly. So what will happen if you have a vacuum chamber? You put a one metal which is contact from outside, and you have a heater just below the metal. Since this is a vacuum, if you apply the heat through the heater, then thermodynamic emission may take place from the metal surface, and where the electrons will go. Electrons will be just knocked out, just like our photoelectric effect. What they will do after that one? The electrons will be accumulated around that region. That is what we call for space charge formation. In this one, the first one, the model, when the space charge is formed, okay, the model what we develop is from the basic of the vacuums or the semiconductor diodes, we call for Seil-Lechmeyer space charge model. We must be realized after this one, then we know that since the space charge is there, then it should be modeled with the Seil-Lechmeyer space charge model, which is defined by the current density is nothing but the applied potential V to the power 3 by 2. Sometimes this is called the J is proportional to 3 by 2 law. Also they used to say different names they used to call. happens in the origin of this space charge theory was founded by Searle and Lumiere, which I've said, from 1911 to 1913, when they reported and derived the space charge limited for this expression. But this happens to be in the inorganic and for vacuums, but this is not true in our conjugated polymer system or in the insulating systems. Okay, therefore, Morguni proposed another space charge limited current, okay, equation for polymer diode, which is similar to the Searle-Lumiere law, okay, which is following assumptions. First one is active layer is trap free for charge injection. Second one is for diffusion of charge carriers is negligible in active layer. Number 3, electric field at the injecting electrode is 0. So by assuming this one, he proposed another space charge limited current equation. Okay, so generally the assumptions 2 and 3 are still valid for most of the organic or polymer semiconducting materials, but assumption number 1, the active layer trap free for charge injection, is further modified with new version as trap space charge limited current model, and will be discussed now in the later here. This is now here when the trap free is not, there is no trap free in the step, then is we call for ideal case, then we call for J is proportional to Morguni derived, J is proportional to the V square. Earlier was J is proportional to J V to the power 3 by 2, which is in the Searle-Lumiere law. Okay, then when we plot here, we can plot the graph J versus this one. For ohmic context, the reasons where can be okay here. In this one, 2 sections. Okay, now in this one, from here to this region, we have seen one is called V omega. The region here is we call for ohmic region, and region above is we call for this is the space charge region where the diode active comes. Okay, this is what we are going to talk here. For this ohmic contract, for this during this region here, the electrode region can be considered as carrier reservoir that supplies a carrier. If the electrode emits more carrier per second than the space charge can accept, the remainder will form a space charge which creates a field to reduce the rate of carrier emission from the electrode. The current is controlled not by the electron injecting electrode, but by the bulk of the semiconductor or the insulator. In other words, by the carrier mobility in this space inside the material. So, now from this ohmic contact to this become for space charge control here, there must be the transition. The transition is we call for trap transition. The trap transition is the one now here. We are here. Generally, an intermediate region is also observed between the ohmic and the space charge, what I just said now here before the Searle-Lumiere. In between the region where the just above the ohmic voltage, then below the space charge dominating, there is a transition there. Okay, region. This region is termed as a space charge region. What I have shown you here from this region, this ohmic region, and this is one space charge here. In this transition is now we will call for limited transition here. This is what we are going to talk about. The charge transfer inside the polymer region is controlled by the trapping and the detrapping of carriers at both energetic and positional distributions. Traps are nothing, just impurity. These traps are nothing but impurity, and they create a state in between in another sense, we can say in between the conduction and the valence band, the trap in between the Fermi and the conduction band, the steps are married. Okay, when the electrons are moving from one to another one, the electrons will fill up. Okay, that's what we are going to talk. Here we see here this region, this is the ohmic region, and this is for the trapping region. There's a Morguni region. Then another one here, this trapping is filling up. Then another space charge, now another control for space charge coming here. This is what we will call here the tree. in the material, do you have how many spacers? All this is it your spacers or your, sorry, is your trap are discrete energy discrete, or all your traps are exponentially distributed, or your traps are Gaussian distributed, okay, or all your traps are uniformly distributed. These, depending on this one, analysis are different, okay. When the traps are discrete, okay, then the slope of this side limit law, after filling the trap, then it should follow the same pattern where this pattern is following the slope of this one, and slope of this one has to be same. This is nothing but this current conduction is due followed by the Moore-Gurney law. If it has only single or multiple discrete energy levels. However, in the case of exponential discrete levels, the ohmic level, the trap limited, this is a trap limited, means trap is starting trap limited more only, then starting filling slowly, filling, then after it, after completely fill the traps, then the conduction will be continue again, then in the conduction, this will be going here. But the slope of this one and slope of this one should be different. This should be more than 2 and this should be 2, okay? But slightly here, the slope is very much low, difference is very low in visibility here. All right. So now here is the current both cases of the which I have to use for model. What are the models we describe here? These are the patterns now we have shown here. Okay. So now next one is now generally we found what is we found here. It's like this. For if the when you plot for v equals I to the power m, m equals 1, then I is proportional to the v. This is nothing but ohmic contact. If m is equals to 2, then is a trap free or filled space, means there is no control from the traps. Then m is more than 2, then we found that some trap is controlling the conduction, means we are not filling the things completely or something is stopped by the traps. Okay, so these are for a trap, generally the power law conduction mechanism, from where we can identify which one is the model I have to choose by seeing for my experimental results. Here we made a device. First one is to see for the theories, what models, what we discussed. We made a device. We made a device for poly-3-methylterpene is electrochemical polymerization on the SS electrode, means stainless steel electrode, which is for the grade 304. The polymerization we made it. Then we made the once we made the film, then we cut the 4 different parts of the piece. Then first one we retain, the other 2, what we do here is this, the S2 sample, S1 sample is now we de-dop once you make the film, and we apply the reverse current for 20 seconds. In another sample, we apply the reverse current for 40 seconds. Another sample, we apply the reverse current for 60 seconds. Another sample, we apply the reverse current for 40 seconds. When we apply for a reverse currents, what we do, the polymer change does not affect. The effect is the amount of charge carriers, means the dopants. We are removing the dopants. Okay, how much we apply here is we are getting here 0.25 milliampere per centimeter square. Okay, so plot time is 4 minutes. Then after we are removing the dopants here. What we found here, we found is now very interesting. Very interesting now here, this is IV curve. This we do the measurement. We measure for IV from the 1, 2 to the say -2 to +2. But we are doing for -1 to the +1 the data we have shown here. But in this one, there is you see the curves. You see the curve pattern. The patterns are not similar. What does this mean? Okay, is asymmetry. A small asymmetry is because of that. When we make the contacts, we are making the steel, polymer, and the silver. The work function of the barrier height of the silver and the polymer and barrier height of the steel and the polymer, they are not equal. So the injection rates are not same. It is showing here. The IV curve follows generally IV curve generally follows the V to the power m. Here m is almost equals to 1. Here m is more than 2. So m is equals to 1, saying this follows from 0 up to the 0.1. We can say the device is following the Ohm's conduction mechanism. but just increase the potential, then we found that it is not the ohmic no more, then it is coming from the trap control conduction mechanism, because since m is more than 2, if it is m is 2, then it's more Grüni, which we know it. Okay, so now here is we are analyzing for the IB characteristic for some temperature. We do up to for 40 Kelvin. Generally, we have the data up to 420 Kelvin, but we are not showing because some in the low temperature measurement. So we do for some selected temperatures. We start from the 40 Kelvin to the 300 Kelvin. We for more numbers, but we are showing this is for I versus V. IB characteristics for S1, S2, S3, and S4. Okay, but here you see in the lower temperature. In the lower temperature, what we found here is that the variation from here to the here variation, this scale is 10 to the power -7 almost here, and this is now 10 -2. And for this red color, you can see for 10 to the power, this is around -9 into 10 to the power 4, -4, and here's here. So variation in the high temperature, the variation of the current in the low temperature, the low temperature variation is high. Okay, so with this analyze, we are finding we fit with our Moore-Grüni law, and we can plot the parameter for L, which is correspond to m+1 as a function of temperature, and we found that one with the decrease in the temperature of the value of L increases abruptly and tends to saturate at a lower temperature. You see, this is 1000 by T. This is the lower temperature region, so this is almost saturated. But in the high temperature region, it changes. So here, what does it mean? Here is the conduction mechanism. Is another one type of conduction mechanism. Here is a conduction mechanism. Is another type of conduction mechanism. Okay. So the linear variation of deviates below 200K, suggesting that different conduction mechanism at different temperature ranges. Okay, and temperature control, space source limited mechanism dominates at the high temperature region. This is the region where we are talking here. This is another curve for here for the current and the temperature at different applied potential. We are applying the potential, we do the measurement. Okay, then what we found here, current increases abruptly at higher temperature region. Okay, you see here this current here in this one, here is almost stable. Here in this section here, this is stable, but in this 5, this is the high temperature because 1000 by T. So in this region, variation is happening in here. So this leads to the conclusion that the different conduction mechanism contributes at a different temperature region. The presence of both extended and the localized state, which might give rise to different conduction mechanism. Okay, for the water conduction mechanism is because of this extended and the localized states. Both are contributing in the conduction mechanism. At higher temperature region, the excitation of the carriers from the localized state to the extended state increases, and the carrier density at the extended state, which ultimately increase the current. As the temperature is lower in this lower section, the carrier may not have the sufficient thermal energy. Here there is no maximum thermal energy to excite, and the concentration of carriers in the extended state reduces to negligible. This causes the negligible change in the current at low temperature. Now here, since all my analyses are, now we are just reported this here. This is analysis of this graph by using the Moore-Grüni law. Once the electric field is applied, what we do, we have to modify the Moore-Grüni law, because Moore-Grüni law, the field dependence on mobility is not involved. So we modify the Moore-Grüni law by considering the contributions from the electric field to the mobility. Then that model is we call for Full-Frankel law, where the J is proportional to the root E. Okay, J is proportional to root 3 by 2. Actually, root E, what is we call for mu is equals to mu naught e to the power some factor into root E. So now the factor root E comes to the picture. So this is the root E dependence here. So now, so in this one also we can say very interesting results is that now here the field dependence is very clearly, the mobility is very much dependent on the higher temperature side compared to the lower temperature side. Okay, so now once we do for electric field dependence, then we found that for that analysis of the AC under the biasing of the electric field. Earlier we use for DC, then generally this is we call for Nyquist plot, or you can call for plot representation for impedance, which we analyze with the system symmetry for the circuit diagrams. Why people used to talk about why you need for this similar circuit, means representative the RC circuits of the cold plot. The reason is that if I want to use as device, I cannot consider as it is a polymer. I should be considered as what is analogy in terms of the active components, like for diode, capacitor, inductor, resistor. So we should be put in the form of this combination so that we can use, or it behaves as an inductor, it behaves as a capacitor, or it is a combination of these things. To be used surely, we have to be identified like this kind of the what is called for similar or equivalent circuit in of the sample as well as a circuit analogy. Okay, so this is the pattern we plotted here, we found here. So we found a similar pattern. What the results we just put it now here is, say, the L in the case what we are talking for this L is coming from contributing from the connecting wires. Then here the RS is nothing but the contact resistance, okay, of the SS electrode. R1, okay, and R2 the resistances in the film. What we see here, and here is Q1 and Q2. This is not C, okay, this is not capacitor. Why this is not capacitor? Because what we do here, if I have a polymer, in the polymer if I dope, when I dope the polymer is just a chain. In the chain, what we do, I put for some ion. Because of the ion environment, it affects to the surrounding. Okay, when you apply the electric field, these surroundings, the one island of the charge is there. When another charge is coming here, then it must be some repulsive or some attractive nature would happen inside the polymer. Because of this one, a capacitor effect may be formed. That capacitor is not exactly the capacitor, but it behaves like a capacitor. That's why we call for, this is Q, this is we call for constant phi element. All right, now this is the device, whatever the prepared device we made it, all these devices in the form of this one here, it is able to explain with this one, this model. Then I apply my theory to another material, which is we call for in the octyl thiophene. Octyl thiophene is little difficult to prepare the film in electrochemical way, because the sticking property is very weak, so it cannot adhere to the material easily. So we do some special technique, but we are able to made it on the, this is ITO classes, and we made it for octyl thiophene devices of this octyl polymers. Okay, we are able to polymerize. Here, unlike for the what is called for the methyl thiophene, here the concentration is increased in the monomer concentration of the octyl thiophene is increases from 50 millimolar to the 140 millimolar, okay, of the octyl thiophene. Now, after preparing, we measure the electrical conductivity. We make the conductivity of the P1, P2, P3 devices. Or these P1, P2, P3 devices are just like that. We prepare the field and we de-dope for 20 seconds, 40 seconds, and a 90 seconds de-doping time. So this is the very few de-dope in charge carrier concentration is higher. There is the lowest charge carrier concentration is the moderate carrier concentration. So these are the carrier conductivity of the samples of P1, P2, P3. So now these samples are here. But when I look for a ratio, conductivity ratio from the P1 from 300 Kelvin to the 50 Kelvin, the ratio is 21.62. The variation of conductivity is very less compared to the others. But in the case of P3, the variation of conductivity is very, very high. So what does this mean? This is saying that conductivity is very high means it has a thermally activated process is already involved, which is we are guessing. Okay, my time is running out, so I'll move a little faster. Okay. Now here we do for IV characteristic. Here the IV characteristic is now almost similar behavior because the silver work function and class ITO, the work function is almost similar. That's why their similarity is behavior, unlike for like SS and what is called our the silver in the last methyl terpene. So the symmetry is behavior observing. Okay. Now, so this is same thing we do for the Moore-Gurney law, and we apply the electric IV characteristic, and we found the mobility. And mobility is now this is for the P2 sample. This is P1 sample. P1 has higher mobility, means higher conductivity sample compared to the P2. But the patterns are similar patterns. Here I'm not able to do for P3 because P3 the okay is not shown here, but is available here. But the ratio also showing for 540 is a higher one here. Then field dependence mobility, we analyze with the field dependence by putting for Moore-Gurney law. Then Moore-Gurney law we applied, and we found that when we plot, there are two types of activation energies we observe here in all this one. However, these two patterns are following the same Moore-Gurney law. Okay, sorry, Moore-Gurney modified to the full Frankel for electrical. Okay, but in the case of the P3 sample, it also shows the same thing, but unlikely the earlier in the P1 and P2, it follows only I is proportional to V to the square, which is we call for the full Frankel model. But here is now another term. P and Q are just proportionality constant. So I is proportional to V term. Another one is I is proportional to V square term. So V term is nothing but when the charge is too low, and there is a control by the moment is also involved. But in earlier two cases, we are not able to see the control from the ohmic because of the conductivity is high. So this is for my slides, which I don't want to discuss now here because these times are not here. So now, what I do here, in highly doped devices, the charge carrier mobility shows a negative field dependence in this one, whereas the positive field mobility from full Frankel observed the moderately doped here, which I am showing this graph here. This is now negative field dependent, positive field dependent, another negative field dependence, which is what I meant here. Okay, so in the case of lightly doped devices, space charge mechanism in addition with ohmic conduction mechanism was observed. Doping level plays important role in the thermally activated mechanism. Okay, so the two carriers of the two slopes in the mobility, here, the two slopes here is saying that there are two different types of mechanisms present active in the different temperature regions. Okay, now despite Moore-Gurney is well accepted, okay, Moore-Gurney is well accepted for the space charge control mechanism, but depending on the polymer what you brought, like for your parameters, what you are involved, parameters what you changing for dopant, monomer, okay, time or the concentrations, then your conductivity will changes. When not only the conductivity changes, the film, the disorder also be changes. So in that time, Moore-Gurney not always be satisfactory to fill it or to use it to define the current model. So in time to time, we have to remodify the Moore-Gurney law, but Moore-Gurney law is we use as a backbone of the transport phenomenon. Okay, thanking you with this one. I open for discussion. But I don't know what to do next.
Thank you so much, sir, for such informative talk. Now the session is open for discussion. We may take a few very quick questions. So, if any of the participants have any questions, please come forward.
Yeah, would like to.
Yes, we thank you, Dr. Jugeswar, for your nice talk. But I received one SMS in my mobile from one of the participants.
Yes,
He's
sir.
asking that this polymer organic semiconductor, what is the band gap? But silicon we are having 1.1 electron volt, but how is the structure of the band gap of this polymer semiconductor? Is asking first question. Second question is that what are the advantages over our normal semiconductors?
All right, this is a very nice one.
Uh,
Band gap varies, not like the what is called organic, inorganic semiconductor. They are fixed. Okay, they are fixed. But here the band gap varies depending on what type of the polymer you use and what type of dopant you use. So we cannot say what is a band gap. It's a very typical one. Still, the people who works in the DFT are also little difficult to tell for this for polymer systems. Yesterday I have seen some, I think Thomas lecture. They work in the DFT. They might be knowing. Okay, but it's very difficult to say for band gap is this. All right. Second one, organic polymers is just what is called used in many places, but the application wise in the case of solar cells, we are very low efficiency compared to the inorganic. But however, for in the case of flexible, okay, flexible display, we cannot use for inorganic semiconductors because they are rigid, they're crystals. Okay, but for this polymer, you can use as a flexible. One good thing is that you can even now the people in Japan they put in a jackets for that one as a screen, or if you think if your mobile phone your display is polymer, then when you fall, there is a very rare chance of breaking your phone and it will work. Unlike for the glasses one, what we use it. Okay.
I will take only there are another 3-4 questions, but I will take only one question. This question is asking that the conductivity is not linear throughout the temperature. There is a variation in different temperature. It seems that conduction mechanism is different. So what are the possible conduction mechanism in the low temperature region, in the high temperature region?
Oh yeah, that's what we are doing. Still, we do not know. Still, we do not know. I can say very frankly, but this is not metal. First of all, metal, as we know, is a well known theory. But since this is a polymer disorder, we are very difficult to tell what conduction mechanism is there. But however, I told you, conduction mechanism, most of the conduction mechanism in this type of polymers is established from the Molteni law, which is originated from Seidel law. Depending on the temperature, sometimes you see here why we do for temperature, because I do one thing. I just wanted to know for the conduction. So example, 5 people are walking on a street. I just wanted to know who are those people. Then how can I do first one? Either I make a barrier, then I make a barrier for say 10 feet. All the 10 feet barrier, all the people are moving. Then I decrease my barrier. When I decrease the barrier very slowly, depending on the size of the people, they will stop coming out. After some time, who knows, only one person may come. Then at a time, oh, I can identify, oh, in this barrier region, only the time the person is coming out, that the person is moving in that speed or in that region only. Similarly, there many conduction mechanisms are there which involve in the room temperature because of thermally activated process, then field dependence, and SARS interaction, column interaction. These many things are possible. But if I decrease the temperature, what happens if the conduction mechanisms contributed from the temperature or say thermal energy will be stopped because they do not have the enough energy. Then I can identify from where this thermal transport mechanism started. Even though the thermal mechanism stopped, another mechanism may be present there. Then I can identify those kind of mechanisms. Say example, electron-electron interaction. Electron-electron interaction is observed in the room temperature as well as in the lower temperature, but you cannot measure in the room temperature because thermonic conduction is much more dominant. Say example, you and the Anil Ambani, when your monies are add together, people will not know your money. Your only people will say Anil Ambani's money. So but your money is also there because you two are together. So this is what we are identifying. So we are identifying by temperature variation. So we do not have the unique theory. So depending on temperature and depending on the field you apply, the theories are different. That's what my topic is. So we are trying to establish what theory may be. Then there should be there should be a unique theory so it can define all this what people are working on. But there's no answer. Okay.
Okay, thank you. As time is very short, we are not able to take many questions, but we thank you, Dr. Jugeswar Singh, for your wonderful talk, for your wonderful examples, for your wonderful understanding giving to our participants. We hope we will be meeting you physically in future. So we thanks once again Dr. K. Jugeswar Singh from our department, from our organizing committee. Thank you, Dr. Singh.
Thank you, sir. Thank you, the physics department of Silchar University, Assam University Silchar. Sorry. Okay. Thank you very much.
Thank you. Over to Glapsa for next program.
Okay, thank you, sir. So we're moving forward to our second and the last invited talk of our today's technical session. So next speaker is Professor Jivanjyoti Das from Cotton University, Guwahati. Professor Jivan Das is currently working as professor in the Department of Physics, Cotton University, Guwahati. He did his MSc from IIT Kanpur and obtained PhD from Inter-University Accelerator Center, Delhi University. Professor Jeevan has a long list of professional profile: a scientist C, Nuclear Science Center, New Delhi; a visiting scientist, Joint Institute of Heavy Iron Research, Oak Ridge National Laboratory, Oak Ridge, TN, USA; a scientist D, Nuclear Science Center, New Delhi; a scientist E, Nuclear Science Center, New Delhi; a visiting scientist, Joint Institute of Heavy Iron Research, Oak Ridge National Laboratory, Oak Ridge, TN, USA; a scientist F, Inter-University Accelerator Center, New Delhi; a postdoctoral research fellow, UNIRIB Center of Excellence for Stewardship Science in Radioactive Ion Beam Studies, Oak Ridge National Laboratory, Oak Ridge, TN, USA; an applied isotope development physicist, National Superconducting Cyclotron Laboratory, Michigan State University, East Lansing, MI, USA. He has association with large number of projects, principal investigator and project manager, DST project on construction of radioactive ion beam facilities at NSc Delhi, a project manager, development of ion source test facility, Holyfield radioactive ion beam facility, Oak Ridge National Laboratory, Oak Ridge, TN, USA, a project manager, Helium Jet Ion Guide System Laboratory, Michigan State University, East Lansing, MI, USA. Professor Jeevan has published about 60 research papers in reputed journals. So with this, I would like to request our invited speaker to kindly take over the platform. Sir, please. Sir, your microphone is off. You'll have to turn on your microphone.
Okay. Oh, okay. Yeah, I think I had to turn it on. I didn't do that. Okay. Again, thank you for the kind introduction, and thank you for inviting me to this conference. It's on nanoscience and nanomaterials as a special seminar. But of course, I would also show this facility is actually the one of the most advanced facilities for nanoscience research. Apart from other things, the accelerators are used for nanoscience. So I will briefly touch on that. So let me first tell that we want to proposing to build up an accelerator facility at Cotton University, which entire Northeast region as collaborator, and then the CUPAC means Cotton University Particle Accelerator Center, and basically, of course, I think the first thing I would like to say is that I worked just after studying here. I went out, and for last 30 years I was first work at Delhi, and then in Oak Ridge National Lab and Michigan State University as the accelerator physicist. So I always pained me that we don't have any accelerator in the entire Northeast states. It's 8 of them. And then I also felt that Calcutta had India's first accelerator in 1950, which Professor Meghnad Saha. So it's called First India's Accelerator. So it was kind of always I feel bad that our region doesn't have. So I finally decided that it is time that we do something. So I came. Anyway, so I will give brief introduction to our accelerator. So of course, first phase we want to do in couple of phases. The first phase is of course the PIMS. The next generation is a positive ion mass spectroscopy. I will tell you what it is exactly. This is the latest generation of radiocarbon dating technique. We can do much more precisely than currently available. For example, AMS technique. And I will show why this is so important. And this is going, if it is funded, it will be India's first and world only second facility. So anyway, we have already written up the proposal. We have got it reviewed also for the phase 1. And you can see all these are collaborators, including Indrajit or Arshad. I see some of the people from the universities. So we jointly wrote up this proposal. I will show what is the status. We wrote the proposal, we got it reviewed. And I would also show some review reports. I think people extremely appreciated. This review is done by all the experts from the nation. So I will show that. And these are the affiliating universities. So this is a joint facility going to be, and I am just speaking on behalf of everybody. So all these our collaborators. So this is the scissor. So anyway, let me come. So I think fundamental motivation is of course the state-of-the-art accelerator facility for the region. So our students get opportunity to explore their true potential. Actually, accelerator is one of the most diverse fields, and it's the most important also. Cutting edge research is done, and for example, you have heard about CERN or Brookhaven National Lab or NSCL, where I was working, a National Superconducting Laboratory. So these accelerators, in fact, India cannot do such big facilities. So India is participating. For example, CERN, India or GSI, the Germany, India pays a lot of money, probably about 1,000 crores we spend so that our students get the most latest technology in accelerator. So of course, if you see in that background, I was quite pained that our 8 states don't have a single accelerator. So I thought we must get it funded because we are putting thousands of crores even for our students to get training abroad or the scientists to go do research. And in this part, of course, we are asking for money to build our own facility for our own students. So anyway, I think that this is the most important thing, that accelerator physicists and researchers in Northeast region. And I can tell you, I have been out all my working life that our students are no less than anybody. So that gives me the confidence that we can do. But also I will show that though it is a basic purpose to train students, but I will show that how we can do unique science. So overall training of our accelerator facility is like this, that we will have the accelerator. Phase 1 will construct a PIMS, positive ion mass spectroscopy facility. And in phase 2, as we go on, we have a 5 megawatt electron accelerator with ECI ion source and 8 beam lines. And these beam lines, of course, will be in the name of each of the 8 states. They will construct and they will jointly maintain here. I believe that we can spread the technology to our students. And then each state is Manipur beam line, Assam beam line, Nagaland beam line, like that. So that is our plan is. And I think people really like this idea. Of course, experimental facilities, some of these things will be India's first. This will be, of course, India's first and world's second. This will be India's first with a ECR source. I'll show you why it is like that. India doesn't have such accelerator. So my basic idea is, even if we are looking after 50, 60 years, we'll make something which will be the top class in India. One of the, it is unique actually in India. And then, of course, we will see even the research using the accelerator. We are going to talk about monochromatic neutron science. It is not there in India. Boron neutron cancer therapy. It is the latest generation cancer therapy. Again, not in India. So I think we will have a lot of really good ideas to work with our students. Then this radiocarbon dating with the PIMS. So we'll show that. And material science. This is essentially nanoscience and nuclear engineering. And of course, nuclear astrophysics. This is, of course, I do personally, the very last one. But okay, let us see the other things. So of course, these facilities also, we don't have such facility, so we need very major infrastructure. So this is the accelerator, essentially the research component of it, accelerator and how we will do it. But even to do that, we will need very advanced support laboratories, radiation detection, target fabrication, beam dynamics, and diagnostics laboratory and ultra-high vacuum laboratories. So these we have to set up as an infrastructure. And then, of course, basic infrastructures are required. These are laboratory infrastructure, like very precision machining facility. Within a micron precision, we have to machine things for an accelerator. And liquid nitrogen, electronics, and computational facilities. And of course, it will also involve constructing a new campus. So users will come. Accelerator facilities run 24/7, like CERN you go, or somewhere you go. You do experiments, you have to run 24/7. So people have to stay, operators have to stay, staff has to stay. So of course we are going to need office space, guest house, and security and everything. So this is what our plan is. And last time giving a brief introduction, our preparation budget is actually about 300 crores. In phase 1, we are going to put the PIMS and material science. This will be of course ready in 3 years if the funding comes quickly. So it's about cost of 37.75 crores. Phase 2 with the new accelerator, as I told all the things, is going to cost us about 200 crores. And phase 3, the experimental facilities, so is about 63 crores. So it's about 300 crores over a period of 15 years. And for each state, I don't think it is asking too much. So anyway, let us see. Let us now go to the science. That is the politics of it. Okay. So actually, accelerators, I pick up this slide from APS, American Physical Society. The accelerators are essentially because it's a tool of discovery. If you see all the modern new Harvard Hadron or anything new discovery, Higgs boson or application, everything actually involves accelerator. In physics, for example, 25 Nobel Prize in physics has come from accelerators, and 22 in chemistry has also come from accelerators. So you can see there are 47 Nobel Prize using accelerators, and this is the highest in any field. It shows how important is this thing, and that is why you can see that why India is putting so much money to even, apart from accelerators in India, if people go to experiment in CERN or GSI in Germany or Brookhaven National Lab, like that, because this is even if we cannot do something ourselves, still our scientists should not be left behind in the science, because this is where exactly the discoveries take place. And then, but of course, staying so long outside, I realized that actually next time century is of course going to be in biology. So our accelerator will also talk about what we can do in biology. I think this is one of the most advanced field in accelerator. This I think physics and chemistry is gone. I think not gone, but I think biology will be more in the next. I believe, and that is what one of our prime focus we are going to put. Because India has also such things are not done, but I think we will start. But first, let me tell you one of the most one of the recent advances for cancer therapy. It's called a boron cancer therapy. This is a targeted therapy actually. So here the radiation only kills the cancer cell, and it doesn't kill anything else. That is the, unlike current radiation, like you do gamma therapy or proton therapy or whatever, they kill everything, kill the cancer cells. When the radiation goes through, they kill the normal cells on the path. But this technique can only, the targeted, only kill those cancer cells. So this is first, is a clinical trial is going on in Germany now, and India doesn't have, but let me tell you how it works. So what we do with our accelerator, we produce proton beam, and then there is a neutron beam. From the proton beam we produce using nuclear reaction, and then it is put on boron. If it puts on boron, then this boron breaks up into helium and a lithium, and these are roughly energies of like 2 or 3 MeV. So they, when they go to a cancer cell, they can only go to one cell diameter. Typical cell diameter they can go. So these are produced in the cancer cell, and then they will kill the cancer cell. Because their range is so small, they cannot kill other cells. So this is basically what happens. Accelerator produces neutron beam, and then the neutron beam is put on boron, and the boron gives these two radiations, helium particle and lithium particle, which kills the cancer cell. Let us see how that happens. So this is, you can see, these are these green ones are the cancer cell, and this is the normal cell. So when we put boron, you inject a patient with boron. So the boron, which is a drug of boron. So this right now the drug is like the 90% is absorbed by the cancer cells and only 10% by the normal cells all over the body. So you can see these cancer cells will have absorbed. We inject boron. This is the human. This is a person. Person we are giving him an injection with boron. So he got this boron. This is a cancer patient. So these are the cancer cells. And these are the borons you have given as an injection, then you can see they have only gone to the cancer cells. These green are the cancer cells. These normal cells don't get the boron. But this reaction I told, neutron coming on boron, giving this radiation only will happen in these cells. Because these does not have boron, they will not react. So the moment we put the beam, then the beam coming, so these normal cells, wherever, they will not be affected. This is going to kill the cancer cell. You can see the beam has killed those cancer cells. You can see these are what these normal cells are surviving. So it is gone out. So as I explained, why it happens, because when this neutron comes, when it reacts with this boron, it produces these two. But these two, helium and lithium, they can only go in the green. After they lose all the energy in this, so they don't go beyond this. So that's why they don't kill these cells. So this is the I think one of the most difficult cancers it can be treated, and we want to, of course, the clinical trial has started in Germany as 2019. So it's a really the latest generation technology, and we want to be the India's first one to attempt developing this. Of course, we have feel little difficulty in the sense I try to get some quotes. They say that they cannot supply because it's a very highly prohibited technology. But I think this gives us challenging. We can actually use our own students to make this. So I mean, I'll show you what we have been doing. Yeah. So that is, I think it's a pretty interesting that way that we'll be everything ourselves. But anyway, so this is a publication in Physics World in 2019 July. So you can see May 17 May. So you can see this is a really state of the art, and we want to be, again I was saying, India's first. We are doing later, but I think we will show the way how to do the most advanced things. So this is what we come up with. This is our first example what we will do with the accelerator. Second example I'm trying to give is the PIMS thing we told. This will be, of course, world second, India's first again, positive ion mass spectroscopy. This is for quaternary geological research. So let me tell you, we have got this letter of intent. We have got letter of intent for this also. So this is from Guwahati University. So what is there? It's a Brahmaputra river. You just think, Brahmaputra river has been flooding for last, and we are not able to control the flood. It is going everywhere. So it is not that you cannot just put engineering problem, just put some boundaries and control the flow. So what the real way to do is, say for last 50,000 years, we want to see how Brahmaputra river was flowing and what was the corresponding climate there at that time. And if we can correlate these two, and knowing that present climate, maybe we can do a better modeling to how to control the flood. That is the idea. So within these PIMS, I will explain how it works. The radiocarbon dating technique essentially is the most precise than any existing radiocarbon dating, like the AMS. So anyway, so with that, we'll be able to take samples from different places and also environmental samples of those times, and then use this like a tip of a pin, that much sample. We can exactly say whether the river flowing will have some particular salts, whether those salts are there or not. And then we'll date it and we'll see where the river could have flown and what was the climate. So this is one application. So they are showing that what level of digging and all has to be done. These are geologists. I don't know of those details, but this is the application. This is what we are going to be able to do. Next, this is again, of course, as I told, this is a world's first. I mean, world second, India's first. So we'll be really having a lot of opportunity. And I want to show about this. This letter of intent has come from Arunachal University, Gumpi Devi Thungar. I'm really glad actually. Means she is saying that some paintings are there very old, she wants to date them, and these are non-destructive. Take the pin of a tip, some sample, and then we'll study. She also says that she will do Raman spectroscopy with that. That also can give. So you can independently, complementary technique, we can use to verify the exact what is the composition of the painting and what is the age of the painting. And actually, this is what I think. Of course, I put a special comment of my own with her is that it says when you do something very first time in the world, you have actually make original contribution. So PIMS combining with Raman spectroscopy will be a very original contribution to science, because this is the first. Most of the time, what we do research is what others have done 50 years back. But when you do first time in the world, like this PIMS, or second time in the world, we can make original contribution. That is what we need your thinking, and this is what this is. I really like this idea of Gumti, Professor Gumti Devi. Yeah. Then we have got another letter of intent from material science from Professor Raj Mohan Singh, Manipur University. Again, using the Pixie setup and with our phase 1, how research could be done. I mean, so these are ample opportunities. I am showing these examples so that you all could also think, we have really want people to use this facility. This is another letter of intent for archaeology. Department of Archaeology has given. They have Cotton University, this Manjil. So this they have gone and done survey in archaeological digging in Tripura, and this is excavation. They have found these samples. So now we'll be able to exactly date them and found a composition, and we can say how the India's civilization, say 30,000 years or 40,000 years or 50,000 years, which compares with the other progress in the world. So we can understand about our own history, and this technique, PIMS, can do better than the other technique I called AMS, actually the mass spectroscopy, in a much better. So that way we will be able to move more precisely these things. So these are all the things I showed are the applications, or some of the applications for the side, the applied research in the kind of understanding of human treatment, or for understanding river pattern, or this history of ours. So this is where they have dug the sample out. Is all these things you can read where this is done. I am just copying their letter of intent. So this is what has happened. I mean, what they want to do. So of course, several more letter of intents are in preparation. 2 on baron-Newton cancer therapy. This is done by Professor Kalyani Borua of Guwahati University and B. Borua Cancer Institute and Guwahati Medical College. I think we want a lot more people to join here, because this is something, as I showed, the most exciting, quite exciting. And target for monochromatic neutron source. This is Nagaland University and Borden University. I am working with them to get this thing prepared. And I really want, if somebody who wants to join, I would be glad that we can join together. I mean, that is why I agreed to give this talk, that we get more people to use this. And the life sciences with accelerators. This is again the Nagaland University is taking the lead. And I'm really glad that we are having all over the region people coming up and taking responsibilities. So now let me tell you what the accelerator will look like. So, excuse me. So, of course, this is the kind of the original accelerator that was there. It is, of course, India also has 2 such large accelerators. So what happens that this is called tandem accelerator. So this is where the high voltage, just think like a normal physics. It is a high voltage here, and then here what we do, we put beam. We make an ion source with -1 charge. Let us say carbon. Carbon has got 6 protons, 6 electrons, and 6 neutrons. So you add 1 extra electron. So carbon has 7 electrons. So that will be charge, that will be -1. So that carbon -1 is prepared in this source. You bend with a magnet, you can think like that, and then you can put a high voltage here. So 20 million volt high voltage is in this region. So this negative ion is 20 million volt. So it will gain Q into V. Q is -1, V is 20 million volt, so 20 MeV energy. Like this, it gets accelerated. That is the definition of the acceleration. So this got accelerated. Then what we do, here we put a foil and take out all the 7 electrons. Then what will you get? You get 6 plus carbon now. Now this 6 plus carbon we bend with a magnet and then bend here, and then of course you can see this is ground here. Now this This is 6 plus, which are 20 MeV. It has got 20 MeV here. They bend and they become straight. They see the ground. They will come out again. It is like a lower voltage, positive to negative, you can say. So again, if they repel by 20 million volt, and 20 into 6, such that is now 6, Q into V, 120 MeV will come out, the beam. So you get essentially 120 plus 20, 140 MeV for carbon. So like that, this accelerator works. And India has, this is called tandem, India has 2 major facilities in New Delhi and in Mumbai. These facilities are there. But Japanese have shown that there are 2 problems. One is, of course, this foil you have here. When you put this beam, this foil starts getting damaged when you put a lot of current. So in the scale, some scale, you can say about 100 nanoampere to 200 nanoampere, beyond this foil will start getting damaged. So you cannot really get high current out of this accelerator because it's limited by this foil, because you are making positive ion here. So you have to take out the electrons. So you need a foil here. This is called a stripper foil, technically. So that is one problem. Other problem is, you also know from chemistry, say argon, neon, xenon, krypton, when the cell is full, carbon you put an extra electron because that p orbital has vacancy. But you know, if it is get 8 electrons, which is argon, the moment neon, the moment it goes there, Z is equal to 10, you cannot put an electron because the cell is full. So those beams, similarly neon, argon, krypton, xenon, you cannot give those beams out of this because you cannot make negative ion. So this is another fundamental problem with the accelerators of this type, and which is actually there in India. Both the accelerators at Delhi, where I work, and at TIFR Mumbai and BRC Mumbai, both have this problem. So the Japanese have come up with this idea that they say we'll put what they call an electron cyclotron resonance ion source. It's a very compact ion source. We'll put it here, and it will give directly positive ion with high charge state, and we can use the beam. You don't use this part of the accelerator at all. Only here on one. And then, of course, it gives high charge state. It gives very high charge state. Carbon, it will give, of course, 6. 6 electrons can be taken out. For example, oxygen, it will give 8. But calcium, it will give 20. Or nickel, it can give 28. Like that. So, and you can see that 28 into V, whatever is the charge state, multiplied by the voltage, will be the beam here. Then this source can give thousands of microampere current. So it is corresponding to this machine. It can give 1,000 times more current because this can give. There is no stripper. So there is no problem. We can directly, this source gives all the current we can take out. So that's what this problem is solved for having high current. Also, the ECR source can give negative ions, these inert beams. So their problem is also solved. So this was in 2011, Japanese have invented this technology, and this is recently commercialized. And our accelerator will be building essentially this part. Our accelerator will be only starting here and this part. And so, though it is half of it is quite compact, but we'll get, I can show, the thousands of times more current than Delhi or Mumbai, what is currently in India. And also we'll get those beams, which cannot be got in India now. So that is why our accelerator will be unique. It will be India's first of this kind. This is what I am showing here. The proposed electron accelerator model as 5U4 for our northeastern CUPAC facility. So essentially, I am showing this part onward. So this part, the rest of the accelerator is very common. This part. So this accelerator, essentially the top part, this is a 5 MV. Here this ECR source is sitting. You can see how small it is. It's about 1 feet. And then it gives the beam and goes out. I mean, okay, I don't want to go into those details. Here I want to show now all the things I have talked, I want to summarize. In this plot, if you see little carefully, I mean, little attention, you will understand. It's very simple, like a 2-dimensional graph you plot in graph paper. I have plotted it here. The x-axis, I have plotted that is a beam current or the beam particles, number of particles that comes out of the accelerator. Like here, what we get eventually for the user. On this axis, I am plotting that. And there is a unit called, I am putting in microampere. This is a current. And it's a log plot. You can see, you can directly read it. And this axis, the energy of the beam. Like I explained, how the energy comes out. So what will be the energy of the beam? I have plotted this here. So first I saw the two two largest Indian accelerator facilities. The Peloton Linac facility at Inter-University Accelerator Center, Delhi. This is India's national accelerator facility. And this Bhabha Atomic Research Center and TIFR at Mumbai. You can see those currents. This is microampere, so this is 100 nanoampere. 0.1 microampere is 100 nanoampere. This is about 80 or so nanoampere I can give current. And the energy of the beam, you can see from 10 MeV to, you can read here, 100, 200, this is 1000 log plots, is about, this is 900, this is 800. So 800 to 10 MeV they can give beam and in this current. So this rectangle you see the pink, and that roughly decides in this two-dimensional plot. You can think like an island. This is the island in which these two facilities can give current. And these two facilities can give users beam only limited to this region. This is not a discovery class facility. Similarly, I will also show a little example that, of course, it is realized that we really need high fluence experiments. There are huge experiments, we need high fluence. And all over the world it is going on. So DST realized that they have funded 2 mega science projects at Prayagraj in Allahabad and Kurukshetra University. These are to extend this research from here to here. A lot of nanoscience. Essentially, these facilities goes on. This is essentially the last couple of years. It was funded purely for these nanoscience applications. These are like 30-40 crores project. But anyway, so again, those facilities you can see. Just see again, read the same way I explained. Read the current. They can go from 0.1 microampere, 100 nanoampere, to like 1000 microampere. But see the energy. This is 1 MeV, this is 100 keV, 200, this is 1 MeV, this is 2 MeV, about 3 MeV energy. This is the island. Those facilities will operate. They can give high current, but the energy in this island. So these two DSTs mega science facilities. So you can see, we really need high current. That's why these were set up. But you can see they are limited by this y-axis. This island is what we can do. So if you in this figure, you can see there is a huge island here which is vacant. And that is what we are planning to do. This our facility will essentially give this all this current in this high range, also the energies. So it will open up a new domain or new island, giving our researchers the opportunity to do research. So this is that basically to summarize what our facility is going to do. So let us now talk about the material engineering. Essentially, this is nanoscience and research. We have the India's topmost nanophysicist, who is my ex-colleague at IISc Delhi, Professor D.K. Avasthi. He is guiding us. So I think I really want nanoscience people to think about using accelerators. Here, of course, I want to give a simple example. One, just what is going on in the world. This is the European Center of Excellence at Paris, France. This is essentially called the Joint Accelerator for Nanoscience and Nuclear Simulations. We exactly have all these accelerators they have. We exactly have the same accelerator. Whatever research they do for nanoscience, and this is a 2019 publication. I will show the results. So it is a state of the art. It is not something that happened long back. This accelerator is very new. This is one of the. Our accelerator is exactly identical. So whatever they are doing in this place for nanoscience, this is a nanoscience community. I want to just think about doing it in here in the Northeast. What is happening in Paris? So essentially, the accelerator beam they use, and then all these devices are these are ion beam analysis beamline, and these are very common things. I mean, it looks little figure-wise, but it's not that complicated. I mean, I work actually on the instrumentation. Anyway, I will show you that. So this is the accelerator, the main accelerator they use for experiments, the 3 MV. We are going to have a 5 MV, so you will have even more opportunity to do experiments. Similarly, they have the again another facility. This Janus, the joint accelerator for they have to set up nuclear nano and nuclear simulation. So of course, I am showing this for specific examples. I told you about DST mega science. This is they have an accelerator in this. They can also get beam at 150 keV. This ion source gives beam. This is what the DST mega science is. The very high current at the low energy part. I will show you that again back so that you can clearly understand. And for example, they do this research with transmission electron microscope. use the beam and do online TEM studies like that, or Raman studies like that. So essentially, okay, I'll come back to the slide again. Okay, essentially this one, I kept this slide just so that this 100 keV, 150 keV, like this, essentially this region. This is what the Prayagraj and DST Mega Science project is about. Prayagraj as well as in Kurukshetra. This region, see, this is 100. You can see this number, it's about 200 keV, which are you can get up to 1 MeV beam, but essentially this facility. So this is what is India's mega science projects. Because of the high current, one can do this research. These two are set up, and this will be our phase 1 actually. So you can do this experiment in 3 years in Guwahati. So anyway, so I have already talked about beams. Just trying to summarize the novel alternative to AMS, and this is the existing technology, and what we have talked is the new technology. And then you have seen how people are already thinking about extending that using Raman spectroscopy. I told I really like that idea. And then investigation of archaeological samples we have talked about, and of course art science and ISRO also has a lot of applications. They get samples from the moon and all. Those has to be analyzed for its life and composition. So all we can do using beams much more accurately than anything else. Any other facilities in India. Okay, and there's of course this DST Mega Science project I just showed that our disk can also give these beams, so we can do this research. So this is our design of our beams. We already had this. Okay, I don't want to go to technical details. ECR source gives carbon, so that carbon 14, and then you know that carbon 14 how it works, right? It's a dinosaur 50,000 years back ate plant. Carbon 14 is there on the plants. It is produced from the nitrogen reaction on neutron reaction on nitrogen 14. Neutron coming from the cosmic ray reactions. So that carbon 14 has got a half-life of about 6,000 years. So those plants and all also get carbon 14 like carbon dioxide. It's a mix of carbon 14 and carbon 12. So they eat those, and those plants the dinosaur has eaten. But after he died, this carbon 12, 14 will decay. Every 6,000 years it will become half. But the carbon 12 will not decay. So what it is done, you take the sample and you measure the carbon 12 current count and the carbon 14 count in the same sample. Carbon 14 has keep reducing, but carbon 12 is fixed. From the ratio, you can say if it is half, or some ratio, you can say that okay, composition is going down by half, it is half, it is 6,000 year old. So if you get only 1/4, you can say it is 12,000 year old. Or you can get 1/8, you can say it is 18,000 year old. Like that, we can accurately determine this. And this technique can do much better than the other technique. That can go up to 40,000 years, and these beams can go up to 60,000 years. That is and also much more sensitive. And how it is done? So this carbon, so that is how this technique works. This carbon 14, in this we make a negative ion first. So the carbon becomes negative ion. Of course, carbon is very small amount. It's a trace element. 14 carbon is very, very small, 1 in billion. But this nitrogen 14 is a huge quantity. That is the problem. Why we did this setup? So this in this what we make a negative ion. So negative ion carbon makes and nitrogen doesn't make. So when it's coming out, say it is like 10 to the power 10 particles of nitrogen 14 will be with 1 particle of carbon 14. But when you make a negative ion, only the carbon will make negative ion. Nitrogen 14 is positive. Of course, the moment you have a negative and a positive charge, you can put an electromagnetic field, and you can see positive charge will go bend in one way, negative will bend in the other way. So we can clearly select the negative ion and accurately date it. Get how many carbon 14 are there very accurately. That is how this thing works. This thing is called the EDMD spectrometer, and this is the ECR source. This ECR source is the same as I have showed. It is a Japanese peletron. So we thought, okay, we'll first buy the ECR source, do this research, and also train our students, and then we'll go out setting up a new accelerator. And as you said, it will be all those research you can do. It will be quite good. I mean, also we'll train the students. Another advantage is that this whole thing is about 15 feet by 15 foot room. So we don't have to really. We are going to use our existing lab, one room take out and do it. The civil construction takes a lot of time. So that we avoid by going for this setup. That is why we have told the phase 1 will do Neutron. It's very compact. That's what it helps. So we'll not have to do any civil construction. And also another, of course, it's brand new. You can do really exciting research. Also, this ion source is same as the accelerator ion source. We notice we don't have any trained people. So we'll get our students to work on this, and they will get hands-on experience with this. So with the 3 years, we use this setup. These students will get all the experience, and they can work on the main accelerator. These are the ideas. That's why we want to do this first. And finally, of course, there is no radiation. This machine uses 100 keV beam. So 100 keV don't nuclear radiation. So that essentially all the problems of regulatory authority and clearance which will come with the accelerator is not here. So these are the reasons we decided, okay, let us do the first phase 1 with the pins. And also, as I said, we'll do important research, we'll train our students, and exactly the ion source we are going to use in our main accelerator. And then, so huge, of course, And then finally, again, I come back, huge opportunity for original research, original contribution. We are not doing something, this is 50-year-old. This is just started in the world. And like already we have got ideas. People are coming up with ideas which are new. That everybody could think and come up with their own ideas. And that way we can make this facility world-class and world-renowned. I mean, it is already world-class. But it will be world-renowned that our innovation will show up. Otherwise, you don't get the chance when you do 50-year-old research. So anyway, with that, this is the modeling. We have already finished the model and how to fit it in the room. So I don't want to go to the details, and then okay. So this is how it works. I don't want to go. And finally, I want to tell a little bit about nuclear astrophysics. What I do before I go to the other things. Essentially, let us see. Okay, I want to quickly go through this. This is very nuclear astrophysics means how the elements are formed in the sun or stars, how it is evolving. Those many data are still accurately not known, and this is one fundamental interest that we understand. This accelerator can actually do from a couple of minutes after the Big Bang what elements are formed, how it is a rate, everything can be done. But the nuclear reaction, the biggest problem is that the cosmic ray background is dominant. So you cannot, most of the experiments are done deep underground. This is a world-class facility, a Luna laboratory for deep underground. I think at Italy, they are about 3 miles below the ground, so that the cosmic rays are blocked. So that is why I do these reactions. This is actually to set up underground there and do the experiments. So we want to, and such facilities are also coming up, new one in China and US. We want to do it little differently. So I want to just give you an example. So for example, Luna proposed to do this experiment. 14 nitrogen coming up on proton beam give 15 oxygen and gamma. It's a very important reaction. How oxygen is formed in the universe. Oxygen is what we breathe. We still don't know this data within 5% accuracy. So that is such a basic thing we don't know. We want to understand. So what they will do, the Luna will do, this is a proton beam, they will use a 14 nitrogen target and 15 oxygen they will detect. Because this gamma they detect for the 15 oxygen, which is essentially because of the cosmic ray background, it gets totally overwhelmed, so they are doing 3 miles below ground. We want to do a technique, new technique called inverse kinematics. What we will do, they use proton beam on 14 nitrogen, we will do the opposite, we will use 14 nitrogen on proton. Then we will form 15 oxygen, then of course this 15 oxygen will have some energy. Then we will detect this gamma in coincidence with this 15 oxygen. This is called fast coincidence. So whatever the background of the cosmic ray doesn't matter, because we will keep this gamma only when this 15 oxygen we detect. That is not, cosmic ray does not have 15 oxygen. So this is a fast coincidence. Within a nanosecond, we detect these two together, and then we can say this reaction has happened. So that is called the inverse kinematics. Inverse proton on 14 is the normal kinematics. 14 nitrogen on proton is the inverse kinematics, and that is what we want to do our facility. And for that we are optimizing. I have some experience with this inverse kinematics. Of course, optics and all are pretty complicated, and I will show that I commissioned India's first inverse kinematics spectrometer, and then these things and the gas target. Anyway, but well, that is the way we want to do. And actually, India doesn't have anybody who has a hands-on experience with this, both the target as well as this inverse kinematics spectroscopy. And I believe we will be able to make a India's national facility for nuclear astrophysics, and that is what I want to do, of course. But anyway, this is how we want to compete with the rest of the world, that we will do the inverse kinematics and overground with this accelerator. So of course, these things I don't want to say, these are all done. So now let us say that how we are going to implement. I mean, the accelerator, of course, as I said, our basic aim is to train the students. So we are going to use only all the projects of the accelerator. We'll put as a PhD project. I also, we have made about 54 JRF. We are asking in the funding to develop this. And these students will be drawn from all Northeastern universities. So those students will be registered in their university, come here and do the facility, and work with us and develop the facility, and they will write their thesis on this. And in future, they will go on working on this accelerator. Now, we really want the manpower to be developed here. Our students should learn and our students should operate this facility. As like the beamline I told, the beamline will be entirely owned by one state and those students will operate it. So this is the way. And we will have actually to help them. We will have some 5-year visiting faculties, I mean recently retired fellows from national labs. And so we will put the students with them. So they will work under each one of the 3 students and we will have faculties. So they will finish those projects, they will do useful work, and then they will get the instrumentation hands-on, and 5 years they finish the thesis and they will be the manpower to run this facility. So it will be entirely run by Northeastern students and the Northeastern people. I mean, that is what our vision is. Then accelerators there will be 8 beamlines. We thought we'll make 8 beamlines for 8 states and each or Northeastern states. This state will set up, maintain, and I have significant hands-on experience with this stuff. So we'll get the students and they will design with us, and then they will make it and they will work it and they will maintain it. So that they really get truly hands-on experience. You don't have to go to CERN or somewhere else to learn these things. You will do it here. This is what our aim is. So this is the beamlines we will do. Of course, the experimental facilities, that will be only in the form of letter of intent. We ask, like already I have shown, I have been giving talks and all, so that we get a letter of intent from the universities, and then we'll put up this proposal separately for funding agencies, for funding experiments, and then, yeah, and okay. So, okay, and then these beams, our first beams, as I was saying that this is the DST Mega Science facility, and then with the beams, we'll be also able to, because that will give the same beam energy, 200 kV beam. You can do all the research that is going on in the Joint Institute of Nanoscience and Nuclear Science. Even within 3 years, I think this will be quite a challenging thing. Yeah. So anyway, for that, I again wrote up about our phase 1. This yellow region I just given, this is the facility going to be in the complete facility. But even in the beginning, when we just get the beams ready, we are going to get this region, like the Mega Science facility of DST. So this is where, because DST has funded those, there's a lot of research to be done. So I also want all of you to think, this nanoscience, using this energy range, at the very beginning, probably within 2 years. As I said, that beams is not going to take any time to construct. We don't have to construct civil construction or no approval problem from radiation. So it should be pretty quick. We have already modeled, every design is ready. We'll get the funding and we'll get it set it up within 2 years. So I think you all really should think about doing experiment now in nanoscience. And you can do experiment, you can see what is going on in this European Center at Paris. Just think about those experiments and we will do it here in 2 years. And these are kind of the beams. I just give an example for all the nanoscience users. Take these beams and the current and the species, and you can see what you want to do. And also, of course, this type of things essentially needs project funding agencies like that. You should have hands-on experiments. So when I was a postdoc at Oak Ridge National Lab in the Universal Center of Excellence, so exactly this facility gives thousands microampere current. Same kind of beam, slightly different ion source. I have developed this optics and the calculation. This is also for the beamline. That's what I was saying. I will get our students who will design and do it together. So we'll able to, using a code called Siman 8, we'll be able to do these things ourselves. And that is what exactly the hands-on experience you read for implementing this phase 1. The beams thing I have shown. If you really see this stuff, yeah, this is stuff. Essentially, all this is essentially the same thing. as we did here. As we did here. So all this some little differences there, but basic principle is same. So I don't believe we will have any difficulty in running this PIMS business. This is the, of course, the results, and this is my paper. You can see that all this set it up. We have essentially got there up to 500 microampere. So 500 microampere to 1 milliampere. Our facility is up to 1 milliampere we can give. So you can anyway you can see this is how these things work actually internally. So I believe there is no issue with us. Similarly, PIMS also need this part. So again, I will show you what we are doing. I'm talking about a phase one. This part. This is the mass spectrometer. Essentially, separate the 14 carbon minus. What are 14 nitrogen plus 1 plus charge state and 1 minus charge state. This is a mass spectrometer, and this is what, of course, yeah. I mean, this is what I did. Well, at Delhi, I was a scientist at the Nuclear Science Center. I mean, this was India's first radioactive beam. But anyway, it basically uses the mass spectrometer technology for nuclear astrophysics. I did, but the basic technology is same. So I believe with this, I don't think there is any complication there. We can get a couple of students and get them their PhD degree in there, and they can do the design and work, and we'll get it working. I mean, I don't see any major status there. Of course, this thing so little result if I get time. The first India's first and probably so far the only nuclear astrophysics experiment. People talk a lot, but doing by hand is a little difficult. I think it is the only experiment so far. But anyway, I think because of that, I was given the Best Scientist Award, and also the same kind of things I did in Michigan State when I was a scientist before I came back to Assam. But anyway, I want to do something for my people. I think that is the reason. But anyway, so this is that part of the thing. So we are telling funding agencies, we know what we are telling, we know what we are doing. Also, we are doing the most advanced technology in India. So give us the funding. And we are doing for all 8 states. That is the, essentially, that is the logic we are putting. We can, I mean, this is what I am trying to say. We actually know that what we are talking, it is not that. Anyway, so how the funding will go, look for the phase one. I am saying, the first year we are just pressing hard to get 4 crores. The starting money we need, and this 35 crore, this it will the capital equipment cost, and then of course later operation cost. So for over a period of 8 years, we are asking for 35 crores. I don't believe the phase one PIMS part. I think this should be okay. And I want to see how the money will go. This is because this is how not projects are done in India, but we are asking it is like that. So you can see the first 8 years, this project, we are asking 35 to 37 crores. This is actually the green. This is your cost of the main capital equipment. We are not doing any building construction or anything. This is the cost of the equipment. See the rest of the money, it is going, essentially you can say, of course, we need a PIMS setup. This is the equipment. The infrastructure we have to develop, of course, this heavy equipment we have to lift, and deionized water we need, and there are a lot of high voltage technology stuff we need. So we have to develop some infrastructure. So that is this one. And then staff salary, we are essentially staffs are basically going to be postdocs and PhD students. That will be our staff. We'll train them. We are not going to put any new people. All these people will be students who will do PhD, and then they will get their research degree, and then they will also work with us in the future. There will be no other staff salary, is essentially JRF. And those senior people we want to take few of them. Of course, this one we don't even need. Then the contingencies. Then this is of course a 5-year operation. So here what I did, see all the research I say, so everybody will have ideas to come up with an experiment and do the research. But then the teacher also has to have a JRF, a student to work with him, his TADA, and his instrument we have to buy. So those things, essentially, we don't want, this is how it is done abroad actually. If you set up a mega facilities, you also get funding for the students and the faculties. So that each project, now to get one JRF, he has to write a project to DST or UGC. I think this is ridiculous. And nobody is, waste of time. And this facility will be built up, and it will keep waiting. And because the student is not getting salary. So I want to, straight away we thought, in this project we are putting that the student, 8 JRF every year we are putting, purely for research. So the faculty, also TAD of the faculty has to come here, go stay here in the hotel or whatever, guest house we make. So TAD, all we have to put for this 5 years. So this is the major money. So we are trying to show that this is what is actually required to do if you have to use the facility. Otherwise you will build it up and it will just lie there. Nobody will use it. Nobody will come with their own money to do research. All these interesting ideas we can talk, but that will be at the end, there is no research. So we are pressing hard. I mean, this is exactly we are proposing, that give us the funding, give us this way. The equipment is not, only you can see even less than half in the pie chart. But this is the major component. We want the students and the faculty to get the JRF and the research instrumentation, research budget, and fund a part of this. For 5 years, so this is that funding for 5 years, the brown color. So we hope if the government will, this is all done like this abroad. I have spent half of my life abroad only. So I believe there's a lot of sense why they do it like that. So that faculty can, actually you can get the best research output. So this is what, anyway, this is what we are planning for this facility. Now, in the meantime, after the report is written, we also got the report reviewed because we wanted to see, because this is going to be India's first anyway, and then how the people think. So we got the national big experts, all the experts from the nation. This is the Indian National Accelerator Facility Director, Professor A.C. Pandey. He was the one. Then Dr. Sandeep Chopra, he is the head of Electron Accelerator at Delhi, and also the AMS, the older technique of the PIMS. He is the India's expert actually. He's India's leading expert in accelerator technology and this. Then this B.K. Nayak, he was the head of division of nuclear physics DRC. Then Vivek Datar, he was the director of Indian Neutrino Observatory and the Tata Institute of Fundamental Research professor now. He's a professor and director. And then the nuclear physics division BRC, he was the head. And this is Onit Gupta. He's again India's leading accelerator physicist. Here for BEC Electron, he's in charge of that accelerator facility. So these are the people. And similarly for the nuclear astrophysics, we want to do so that we had this person to review us. This is a route that all the neutron science stuff I have talked about, the boron neutron therapy as well as the other neutron things. So he is the one who reviewed our proposal for that. And this Maitreyi Shah Sarkar, she is the head of nuclear physics division in Saha Institute. She also an astrophysicist, eminent astrophysicist. So they all reviewed our proposal, and this is the actually India's founding figure in accelerator material science and nano engineering. Dr. Avasthi, he is our, of course, he was my good friend. I was working with him in the past. So he's reviewed our nanoscience proposal. So, and I just saw some of the reports. So this is the Chopra report, actually you can see here, but anyway, it is difficult to read. But all he's saying, he agrees that this is going to be world's second in India and India's first, and this is a really superior technology for PIMS. That's what he says. And he also says somewhere that the material science, somewhere he says that we should concentrate on the material science, that phase 1. That is how we have come up with this, asking for a letter of intent in material science. I prepared those 2 slides. So according to his advice, he said that you should go for this 100 kV material science. A lot of nano engineering can be done, and you do. So I put those 2 slides with the beam current and everything, essentially his advice. And he is actually the, India's leading figure. Then this is the report from Vivek Datar, TFR. That he is like says that it is really good. I mean that it is going to be India's first and the world second. So there will be a lot of research with PIMS to start with, and then also local users can do original contribution. That was his report. So then we got this Onit Gupta, this TFR BRC. He is again a leading accelerator expert, and he also, says that this will be really world-class facility in India, and then this research program, we have the letter of intent what we have given him. So he reviewed them, and he thinks that these are really good ideas to optimally use this facility. And this is his, I directly cut and pasted. And these are his, of course, his comments from Onit Gupta. But anyway, so that is, I think I wanted to basically tell about our technical part. A little bit also, we have been, all these letter of intents have come, and this talk is also part of our outreach, that we want all the northeastern states to be involved in proposing experiments. So I have given a talk in this NCR-AST a lot of students were there. Then I have given a talk on this Imphal, Manipur University, for just how their proposal has come out from Manipur. I also give a talk at Nagaland University, and that's why we have got 2 proposals from Nagaland. And then today's talk. So I hope I essentially showed you that we can do really nanoscience. What is going on in the European Center of Excellence at Paris? We can do all of that. So please, I hope we'll get one letter of intent coming out of this talk. So of course, implementation wise, let me say a little bit. So Cotton University is a piece of land. So we have got one part of the land for our facility. Administration has given us, so we can set it up. And then this is where we have gone and surveyed the area. So we think it is quite suitable because there are a lot of AERB regulations, Atomic Energy Regulatory Board. So I don't see any problem there. I mean, this land is good for that. Of course, a little bit more than I can tell that this instrumentation is involved. Okay. Yeah, the nuclear astrophysics part essentially I want to concentrate because this is what I want to do. So this is the S17 measurement we have done. This is a published paper. Essentially, what it means is that neutrinos coming out of the sun, solar neutrino, when you measure the high energy spectrum, we are able to get half. Then, for example, what is needed to for a model to work. So there's a lot of discrepancy. It is called solar neutrino anomaly. And then at Delhi, this is the first project I showed I did. First experiment we proposed in India. This essentially those neutrinos come essentially 8 boron decay. 8 boron decays to 8 beryllium, which is emitting beta decay and a neutrino. And that neutrino spectrum was the problem. So what I proposed to do was that why don't you produce this 8 boron in the lab and directly measure how much it is decaying to production means we use this reaction. The sun also just produce 7 beryllium on a proton, capture produce 8 boron. So we thought we directly will measure the 8 boron and tell what is the rate. We don't have to measure the neutrino because 8 boron is only decaying into neutrino. We thought, okay, let us measure to produce the 8 boron directly in the lab and then measure how much it is produced. And we know each of the 8 boron will decay to neutrinos. So that was the experiment we proposed and did. It involved, of course, this beam 7 beryllium, which is a radioactive beam. It means it is not necessarily available isotope. It's about 52 days half-life. So anyway, so for that, we had to do, of course, a lot of development. That was the DST project. It was, I wrote, well, I think I was in 20s. I was a scientist there, but I come up with this idea and I thought, okay, we'll do. But anyway, I think this experiment made a lot of all over the world. It gave us some good thing. And so I'm showing that how international recognition. So this is one from example. Listen, many people uses it. I just was looking, say, this is from the Moscow Theoretical Institute. And they are using our data. They all refer to our data and use it in their models. Similarly, this is another group. They show our models. In fact, yeah, there's another publication you can see. This is Das. There are not very many experiments in India you will find which is done in India and referred, I mean, by name, the data or whatever. But anyway, so but what I'm trying to say, yeah, okay. And see, in fact, I want to show one more thing. So this is our data. You have seen this paper. This is from the Moscow Theoretical Institute. Their director and they are published. One of the things they say, this paper is states that our theoretical parameters reproduces the measurement by Das et al. I mean, this data is so unique that you cannot just do theory and get arbitrary parameters. Your theory, I mean, it is like if this data you use, if you do parameters, it has to, I mean, so that it satisfies our data. Otherwise, I mean, that is what, I mean, it's quite a high-level accuracy experiment actually. So anyway, so this was a good comment I found. I thought I should share. Similarly, these people also say that this data, when this is published, they say that this is their data. They say they clearly tell these people that, yeah, we have some similar technique. So their experiment consistent with our experiment. And similarly, this is a recent review article nuclear astrophysics. It is published in 2000, you can see 18. So they also, it is the only experiment in India which is actually get a referral there that this is the data that has come out of Delhi, this experiment. And this is what I was trying to say. We have so many people talking about nuclear astrophysics, but at the end of the day, the only experiment was done, we did it at Delhi. And so I believe we'll be able to get this funding here to our facility. And then, of course, yeah, so I want to show that these are the kind of instruments we have to develop for that experiment. It's complicated, but not a whole lot. I mean, these are all, one has to, this electric ED is a spectrometer. That's the same thing we are going to use in PIMS. Similar thing, it's a much smaller scale. So that's what our claim is that we'll be able to do that because we have already done this and showed that for nuclear astrophysics how it works. And this is the only astrophysics experiment in India actually, as I say. Yeah. And then of course these things how it works. So these are the all instrumentation. This is for our nanoscience people. I can tell you what happens. This is a polyethylene target. When the beam falls, this polyethylene burns. So what this device does, you can rotate the target and move up and down. Beam is fixed, so you can see as a broad area of annular region will be giving the beam. So the beam cannot burn the thing. So you can speed, rotation speed and moving up and down speed you can adjust. So the beam when comes, it's a very high flux beam. That is a problem. The target get damaged. But this is how we can solve this. This is the instrumentation we developed. These are all published, of course. Similarly, this instrumentation is developed for working at liquid nitrogen temperature. The target is cooled, so that you can get a lot more gas target, lot more density is proportional to the inversely proportional to temperature. So you can get a lot more molecules for the same pressure. So this is what we have developed. All these things, of course, we have to develop instrumentations. These are all published, and this was at the time when we published 7 beryllium for this experiment. That's why I think our data is very high quality, 99.9% pure. So this is the time of flight. You measure the time of flight for a given distance. You know, if energy is fixed, the time of flight should be fixed. D is equal to T, essentially V is equal to half mv square is equal to E, and then you can measure the V, energy is fixed, means E is fixed, and also for a particular particle only. So you can see here for given M, this is a beryllium M. You can see it is a log plot. These other impurities are there, but it's almost like 99.9% pure. We got 7 beryllium to do that experiment for it, boron for astrophysics. This experiment is kind of like a benchmark experiment for nuclear astrophysics. Okay, I think this is all I wanted to tell. I don't think I have anything to conclude except requesting all of you to come up with some experiment and let this facility for Northeast be used up properly. Thank you very much. Yeah.
Thank you so much, sir. Now the session is open for discussion. Yeah.
Actually, Professor, we thank you, Professor Jivanjyoti Das. Actually, this proposal meeting we had been doing since July. Many meetings we have done. Then I request Professor Jyoti to give this presentation in front of the academics people now. Around 100 people are here since yesterday. So I took the opportunity, requested Professor Jivanjyoti Das for giving this proposal so that people who are working in the material science, particularly nanoscience, they will be knowing such kind of project is coming up and they will be happy to use this facility. I also request to the material scientists, research people who are working on material science to use this facility, come up with the proposal. We will consider it. Surely we will get this project. Now I request to faculty members and researchers to give any feedback or any discussion. This particular lecture is a special lecture for discussion. So any faculty members or researchers who would like to say something, so please kindly come up in 5-10 minutes, please. Dr. Tomba is here or not, sir? Hello, Dr. Tomba. Dr. Tomba from South Korea. Dr. Tomba.
Yeah, I'm here.
Yes, yes. Please, sir, can you give some your opinion about this project, how it can be used, and how you can contribute for our country, sir? You have a lot of experience in this field, sir.
Just now I'm writing a set. Thank you, sir, for your wonderful presentation. I mean, let this project come soon, and if it is coming through, then it will be very useful for the whole Northeast, not only that for the world also. It's coming. If the vision is coming true, then it will be the great contribution to the scientific community in the world also, not only for the Northeast. So it is a very, very good chance for the Northeast people and for the Northeast students and researchers and scientists. That it comes true, sir. I really appreciate your approach, your mission. I really appreciate, sir.
Thank you.
I request Professor Atri to say something about this project, madam.
Thank you, Professor Rama. Actually, this accelerator facility, if really it comes up, it's coming up as is evident from Professor Das' communication. It will be an excellent opportunity. I think basically I am also a particle physicist, though not experimentalist, but we can really think of something, and there are solid state in our department as far as we are concerned. There are people who are working in biophysics and then nanomaterials, and these things will be really helpful for us, and we don't have any people working in experimental physics area here, but we can, if a facility is available in nearby, because we always think that they have to go this way, that way, and there are lots of issues coming up with that. But once that such facility is there within our reach, then the scenario is going to change definitely. And as he has already told that lots of works can be planned, and once such facility is being cordoned up, we can really plan experiments and really do it in a collaborative way. I think so. And I really thank Mr. Jivanjyoti for this much of information being shared with us. And I hope the students and the younger faculty members will pick up something very soon. Any project, even it's a small project, I think it's not a bad thing to start with.
Correct, madam. I request from IISc Bangalore, Jugeswar Singh, if he is there, material scientist Jugeswar Singh from IISc Bangalore. Hello, material scientist Jugeswar Singh, if he is around. I think he's not around. So,
I'm here.
Yes, yes, please, sir, please give some your thoughts about this project and your future feelings, sir.
It's very nice. I am very surprised that few people are trying to make up new facilities in around the Northeast. This will be very helpful, not only for the Northeast people, for around the world. And I am very sure this will change the scenario of the Northeast, what is called research people, especially in the particle as well as for the condensed matter physics and even chemistry people also. So, are you? Is it the timeline what you have given? Is it possible to do it? That's why I was a little doubtful.
Yeah, actually, okay. I mean, the design is actually technically it is entirely possible because, for example, these things I have especially made those things by my own hand. I'm like more like a mechanic than a physicist. I call myself because I make these machines. We have seen all those things I make by hand. So making wise, getting it running, I don't see any problem.
Oh, wow, sir.
Yeah, when the funding wise, I believe for phase one, we have also say that 35 crores out of this 15 crores for the roughly for the capital equipment and rest for the user. I think for it is that we have got all this feedback from the BRNS and this DAE people also. I mean, we have been only several dozen meetings with these people because they wanted to also understand how we are doing. And I think that this is very positive. They believe that Northeast, the government is inclined to fund a major accelerator facility. But it has to be a very quality proposal. Otherwise, nobody is going to put this kind of money. So, but I am hopeful. So first thing, the teams. If the funding is given, we are asking for 4 crore from next year. Actually, behind us, we are applying like this, saying that we have already got it reviewed. We got the best possible reviewers in the country to review the proposal. So while your review may take its own time, give us the first installment of 4 crores. So that we set up the infrastructure, and your review takes 1 year. You come up with, by that time you will finish the developing the infrastructure.
Wonderful,
And
sir.
no review has told that there is anything wrong with the concept. So that's why we are asking. So if they take 1 year to review, but give the first installment quickly, because you have already got it reviewed, and then we have the hands-on experience to do it. So I believe that we can do it in 3 years, actually, finish these films and start this research. I mean, the first phase.
Great, sir. Congratulations to you, sir, and best of luck, sir. I'll be very happy that even Northeast, the new generations, you are doing something for the new generation. I'm very happy. I'm very proud of you.
Thank you. Actually, I can tell you one story. It really pains me. I last 15 years, I was a staff scientist at National Superconducting Laboratory. I left. Of course, my wife is in India. I mean, that's why I had to come back anyway. But basic story is that one person I saw it, he was congratulated for having Nobel Prize. I think he's from Stanford director or somebody. He got Nobel Prize. He was so smart. He got Nobel Prize. And the thing he said, it's not like that. He told I was a student and I was able to work with the Stanford Accelerator while I was a student. And then the college I went, high school I went, college also I did experiment, PhD also I did experiment. Like that, this machine now I know hands-on everything. So when I think about an experiment in physics, I could really decouple the instrumentation and all from the physics. But there's
Exactly.
people who come to do experiment like they're more smart people than me, but they get overwhelmed by these technical things. So their physics potential they cannot use fully. It's a really actually experience. Our students are also as bright actually. I can tell you, I really feel that way. And we don't know, once we have these students to work hands-on with like setting up beamline, setting up experiment, I believe some one of them are going to make us so proud. We do something which we don't think of. And I think that is where we have to give that opportunity to our next generation. I mean, that is what I believe personally. They
Exactly,
will
sir. Yeah. Your
we
belief
will
will be true, sir.
can do, and we'll all realize that they will make us proud. I am sure about that. But we have to give them this tool. I mean, that is what my basic motivation is actually going forward. And I think we can, yeah.
Yeah. Yeah. Thank you, Professor Jiban Jyoti. I pray God for your good health and for your dream comes true. We all around with you. When I first had interaction with Professor Jiban Jyoti in the month of July, I was feeling so much immense by his logistic support, encouragement, and dedicated to the science. I am very thankful to Professor Jiban Jyoti for accepting our invitation to come up on this platform and has given a wonderful talk, sir. Once again, I thank you, sir. So now I hand over to Kulapcha for further proceeding. Kulapcha, please take over the floor.
Thank you again. I sincerely appreciate the invitation and opportunity to talk with you. Thank you.
Thank you so much, sir. So with this, we have come to the end of our 2 days international webinar on nanoscience and nanomaterials. I hope the participants has got benefited by our conference. So now I would like to request Dr. Himadri Shekhar Das to give the concluding remarks. Sir, please, over to you. I think sir has
Himadri, sir. Himadri, sir. Hello.
Yeah, I can see his account there. I guess he left the meeting. He will join or not.
He just called. He is joining.
Okay, okay, sir.
Yes. Marty, sir, the floor is to you. Marty, sir.
Okay, we may wait for a while.
Thank you very much, sir. Yeah,
Yeah, he is
thank you
there.
very much, sir.
Yeah, my connection actually disconnected, so I could not connect. So thank you very much. Today's the international webinar on nanoscience and nanomaterials is organized as a part of Silver Jubilee celebration of the department. I would briefly tell you the overview of the seminar. Nanoscience is an emerging area of science which involves the study of materials on an ultra small scale and the novel properties that these materials demonstrates. Nanoscience has the potential to reshape the world around us. It could lead to revolutionary breakthroughs in fields ranging from manufacturing to healthcare. The area of nanoscience, nanotechnology, and nanomaterials is a fast developing one. In a molecular biology, nanoparticle applications have become an increasingly popular technique for the separation of biomolecules, namely proteins, DNA, and RNA for genomics, proteomics, or metabolomics. The objective of this webinar is to provide an online platform for exchanging and sharing scientific knowledge and the new and fast developed branch of science. I hope the objective of this meeting was nicely actually maintained. For this seminar, we are very fortunate that 5 eminent speakers have delivered their presentation. They are Dr. Laizam Tombasing from Pohang University of Science and Technology, South Korea, Dr. Syed Arshan Hussain from Tripura University, then Professor Sangam Chatterjee from Justus Liebig University, Gießen, Germany, Dr. K. Jugeswar Singh from Indian Institute of Science, Bangalore, Professor Jibanjyoti Das from Cotton University, Guwahati. Speakers have given excellent lectures in last 2 days, and the interaction with the participants are also up to the mark. So in this particular conference, about 191 participants had registered for attending this webinar, and we are very hopeful that about more than 100 participants attended the lectures. So I again congratulate all for attending this webinar and make it a grand success. Over to coordinator, sir.
Thank you so much, sir. As this conference was a part of our Silver Jubilee celebration of our physics department, so we'll have series of events upcoming. So we hope to see you all soon in those events too. And with this, I would like to hand over the mic to convener, sir.
Thank you, Galapsa. Now we are ending the seminar. So I request to our chairperson, Professor Ati Desamukhya, to declare the seminar is closed. Professor Desamukhya.
Actually, a very good afternoon to you all. And we have really completed 2 days very fast. So all 5 lectures were very, very interesting, and I have attended all of them actually. And I hope the participants have got immensely benefited from these lectures, which has thrown light in different aspects of not only nanoscience, nanomaterial that way, more than that actually. And Professor Jibanjyoti at last was giving you a new opening rather for accelerator physics in Northeast India. So people may got interested and they can pick up research in that area. And I would like to thank all the speakers from within the country as well as abroad for sparing their valuable time, sharing all their knowledge with the participants. That is the webinar all about. And as Gulafsa has already said, and I have said in the inaugural session, that we are organizing a series of events to celebrate our 25th anniversary of this department. And we have a YouTube page which is named as Assam University Silchar, Department of Physics, Assam University Silchar. So you can please subscribe that, so that you can have first-hand information regarding our events. And moreover, we will keep you informed about the events that are coming up. And I hope you have enjoyed this event quite a lot. I would like to thank you all all and each and everyone associated with this event, Professor Chatterjee, Professor Jivanjyoti, Professor Arshad, uh, everyone. And like, we are really thankful to you because you have spared so much of your time preparing the presentations, preparing for this particular webinar, and that is how the participants have got immensely benefited from the whole discussions because transport phenomena, then these polymers, different aspects of this nano scale materials. So I would like to thank Professor Tombashing, Lesram Tombashing, and then Professor Shangam Chatterjee, Professor Arshad, Professor Jugeshwar, and Professor Jivanjyoti again for being with us for in our celebration of the 25th year of the department. And I also like to thank the participants to be here with us, and the organizers, the university authority, everybody who were with us for each and every event we are conducting. I would like to thank them all. And with this, I declare this 2-day seminar to be closed. Over to Gulab sir. Over to Gulab sir.
Yes, ma'am. So we'll conclude the meeting here. Thank you everyone for joining us. Ask me.